Welcome back. So next I want to talk about what is static code analysis in the first place, actually. So static code analysis you can also think of as a so-called white box analysis. The important point is that you want to inspect the source code and automatically want to determine certain properties of the program implemented by that source code, but without executing it. That's where the word static comes from. So here we are really talking about analysis without execution. Opposed to that, there is also dynamic analysis, which very often then is a black box analysis. So that basically means you are poking at the running program, you are observing what a program does at runtime without actually inspecting its internals. Like I said, in the static part, in the static view, the important point is that we will not be executing the code. So you can think of it as the following. You take as input into the analysis, let's say a Java program or C++ program or Python or whatever. Then it's being processed by the analysis without running it. And then you actually get some report. For instance, the report might tell you that you have certain optimization potential in certain areas, or you have security vulnerabilities that ought to be fixed, and so on. But there are also other uses of static analysis. So for instance, one use that has been there for many decades and actually was very popular in the early days of static analysis is compiler optimization. So this was to obtain more efficient bytecode or even machine code. So the idea there would be that you take some version of the program as an input, for instance, as a jar file. You then apply your optimization, and for instance, you get a smaller version of the program that has eliminated parts that cannot possibly execute, or where things have been optimized for performance and so on. Like I said, this used to be very popular, and in fact, static analysis is also still used nowadays within just-in-time compilers to some extent, but few people still do ahead-of-time optimizations for languages such as Java, exactly because the runtime environments, so the just-in-time compilers, have become so incredibly good at actually optimizing the bytecode that it makes little sense to try to already optimize things before the execution. And that's why the focus of static analysis has also shifted a bit. So if you look into current papers that are out there, you will see a lot more research on coding support. So that basically means bug finding, vulnerability detection, and so on, like you see here. So that would also be a very simple static analysis on the top that shows you that a certain variable, for instance, is never used. And like I said, so here you would basically insert the program into the static analysis or apply the static analysis to the program, and then you would get some warning messages out of this. And this can be done, of course, also for bugs and security vulnerabilities, and there are various report formats now that people use to actually bring such results also closer to the developers. So we, for instance, ourselves have been working on integrations into various IDEs. And in fact, we have a framework called Magpie Bridge that allows you to very easily integrate various static analysis tools into various IDEs. But there are also integrations into continuous integration and delivery pipelines so that you can actually also look at reports, for instance, in terms of pull requests. That often makes a lot of sense. That when a pull request is being reviewed for integration, it's not only being reviewed by a given programmer, but also by an automated static analysis tool, so that you can make sure that potential flaws in this pull request are actually found before that request is being integrated. Static analysis, opposed to dynamic analysis and related methods, has the big advantage, like you can see here, that it can be used very early in the development process. So you have to have some code to analyze, so you cannot really use static analysis in the requirements phase yet, but you can use it during coding time, and you can use it in particular at a time where not the entire application does exist already, and therefore where you wouldn't be able to just run the artifact, the program, because it's not runnable yet, right? I mean, you only have fragments of the code. In many cases, you might also might want to analyze a framework or library in isolation, or an application for which you don't yet have an implementation of a given framework, so you only have partial code. And all this can be done, at least to a certain extent, using static analysis, but you would not be able to do it dynamically because the code would not be able to run. Luckily, what you see here is that if you do this, so if you apply static analysis and related means in your software development lifecycle, then you have the opportunity to catch bugs early. So you can find them at this stage, and this means that the cost of fixing these bugs is actually relatively low. So there are many studies that have shown this. This here is a graphic by NIST, the National Institute of Standards and Technology in the United States. But all of these studies basically show a similar curve. So the later you actually get to fix a certain bug or vulnerability, the more cost this is going to incur. And you can imagine, right? So if you have to fix something in production code that has already been deployed to customers, that can be horribly expensive, right? That can mean that you have to roll out hotfixes in different versions and variants of your program. You actually have to get into touch with your customers. You have to also rate how severe the problem is so that they can know how to react to this problem. And it's basically all a big mess, and it becomes very expensive. And it's much better if you can find bugs early in your programming, ideally already at the time at which the program code is being written. And these are, in fact, technologies that we are working on in our research. And these are also technologies that you are going to be taught in this course. So at the end of the course, you will be able to not only understand, but also apply technologies or create technologies that allow you to exactly have such static analysis that run, for instance, directly in your integrated development environment or your CI/CD pipeline, so that you get instant response times, and programmers can actually fix bugs early as they are being found. Why else should you care about code analysis in general? Well, it's important for security, for instance, right? So I want to show you one example that relates to Java security issues. Luckily, this is a few years old by now, but around 2012, there was a lot going on with Java and insecurity in Java. So what you see here is a screenshot from a news message on August 30th, 2012, where Oracle patched some vulnerability in Java 7. And then a day later, it was found out that there were new vulnerabilities of a similar kind, also in the same Java runtime. These vulnerabilities were then drawing worldwide attacks, so that was really becoming serious. Then some months later, Oracle again released a fix for this. So there was a fixed version of the Java runtime. And again, just a day later, Homeland Security advised that you should still disable Java even after the update because they still hadn't fixed it entirely, and so on and so on, right? And so the problem was that there was a back and forth. Apparently, there was a not very systematic approach. And in particular, there were many instances of a similar problem in the Java runtime that back at the time, Oracle was unable to find and correct efficiently. And by now, they have invested heavily into static analysis. They've also collaborated with us to some extent on this. But it shows you that there were problems, and there are also many cases in which there still are problems, and these need to be dealt with. And many of these problems, they can be found through code analysis. Another important bug where you can see this is Apple's so-called go-to-fail bug, which you can see in a screenshot here. What you see here is an excerpt of some very security critical code. So this was code in the macOS operating system, and I believe it was used for automatic system updates. And what you see here is basically meant to be SSL certificate check or TLS certificate check. So basically, the client, so the macOS installation that you may be running on your machine, it's checking that the server certificate is actually correct. And if that check is not working correctly, then you can drive so-called man-in-the-middle attacks. So somebody else could try to make available to you an incorrect or insecure update that can then be used to exploit your machine. And if you look at this code, something might stand out to you, or maybe not. At least people at Apple had overlooked this for a long time. The problem with this code is here. So you have a double go to fail, which means the first go to fail will become active if this condition here is actually true. But even if that condition is false, the second go to fail will become active and you will jump here nonetheless. And go to fail is actually a bit of a misnomer here, because what this means down here is it doesn't really make it fail. It means that you're actually jumping over the remainder of this verification or validation routine here. So in the end, that meant no matter what, there were certain parts of the certificate that were never being checked. And that was a big security flaw back then. But the point is, if you look at this code down here, anything that you see within this if statement, and also everything down here, that is so-called dead code. That is code that can never ever execute. No matter what happens up here, you will never jump to this code here. And in fact, good compilers, they will actually find this through static analysis, and they will actually warn you about this. And if Apple had enabled such warnings and looked at them, it might have looked a bit fishy to them that there is security critical code that is actually dead code, right? So if you see anything like that, that should be a red flag to you, but apparently here this was missed. So this could have been very easily found through static code analysis. Another very famous, or I should maybe say infamous bug that really shook the internet a few years ago was the so-called heartbleed bug. So the heartbeat bug was a bug in a so-called heartbeat feature in OpenSSL, which is still one of the most widely used crypto libraries. And in particular, it's used for many TLS implementations. So whenever you connect to a web server nowadays, it's very likely that you're actually using OpenSSL under the hood. And this feature was working as follows. So it's called a heartbeat. So it's used to figure out whether a certain server is still active or not. And so you can send the server a message. You can say, hey, send me these 6 letters, potato. And then the server will basically see this and it will respond, okay, I will send you these 6 letters, potato. And you can do this also with other messages, right? So you can say a 4-letter message called bird, and then it will send you bird. But as an attacker, you might also want to try the following, and that's what people actually did back then. So you might want to say, okay, server, send me 500 letters, and the word I want to receive is hat. So it's only a 3-letter word. And because of implementation issues in the OpenSSL library, that's what OpenSSL would do. It would send you the 3-letter word hat, but it would also send you 497 additional bytes that were sitting in memory. And that's a big problem because in many cases within that memory space, and you could actually set this value to as high as 64K, I think. So within this chunk of memory, it was very likely that attackers could actually find some secret keys that had been used to establish the connection to the server. So using that information for attackers, it would have been able to crack open encrypted SSL traffic and sniff on it, and even decrypt traffic that had been monitored earlier, depending on the configuration. So that was pretty bad, and luckily for many servers, it was fixed within a few days because this really was in the press worldwide. Unluckily, there are still many servers actually vulnerable to this vulnerability nonetheless. So this, I have to admit, it was not found by code analysis, at least not by static code analysis, but actually by fuzzing. So there were people bombarding OpenSSL with different inputs and also potentially malicious inputs. And that's how they found that something was not going right when they then used appropriate inputs like the one I showed to you. But this could have been found by code analysis because it's basically a buffer overread, and that can be easily recognizable in program code, and static analysis can be written and have been written to detect such problems in source code. What's also interesting is that when companies think about software security or securing their systems in general, they often still think about securing their networks, right? So they would buy a big firewall and they would think, okay, nobody can actually enter the system. But this is not how it works. So there are actually statistics that show that this frequently isn't working, and people bypass these firewalls and network security measures, and they enter the system nonetheless. And to show you one very prominent example of this, I want to show you one slide set on a somewhat older attack, but was very prominent because it was actually an attack on the company RSA and a US weapons manufacturer. And so you can imagine they were actually after weapons manufacturing plants, like you can see here. That's what the attacker wanted to get their hands on. And these were actually sitting in a highly secured network. So there's a company called RSA that actually produces these tokens that you can see here. And it's basically two-factor authentication system, which you may have seen from many websites by now, right? So the idea here is that in order to log into this network, you not only need logon and password combination, but you also need to have access to such a physical token. And the way this works is that basically this token has a secret key embedded. And based on this secret key, every minute or so, it will generate a new pseudo-random number. And the server here, it's equipped with the same secret key, so it can generate the same numbers due to that secret. And then during logon time, you're comparing the two, and only if they coincide, you can actually log in. So what the attackers did now, they actually sent a phishing mail to this company RSA first, that is actually producing these tokens. So they actually exploited here the fact that there was a zero-day vulnerability in Adobe Flash Player. And back then, it was actually still possible, and maybe it still is even, I don't know, to have Flash objects embedded in Excel spreadsheets. I don't know why that would ever be a sensible feature. But back then, the feature existed. And so basically, these RSA employees were coerced to open an Excel spreadsheet that would then itself open this Adobe Flash plugin and actually, through this vulnerability that you see here, inject the so-called poison ivy Trojan horse onto machines of employees that work for RSA. Then, and that's something that's very commonly done in these kinds of attacks, in the next stage, they did so-called digital shoulder surfing. So they were basically looking across the shoulders of these employees, but virtually, right? So they were monitoring what's going on their machines. Do they have access already to the information that we need? And if not, can we infect other machines in the same network, machines by people who maybe do have access? And that took them a few days. In the end, though, they were able to collect the secure ID secret seeds of these tokens. So that means they were able to manufacture these numbers by themselves, basically, right? So they would be able to break into any network that was secured through RSA. And here one has to say RSA as a company reacted actually relatively quickly. So after just a few weeks, they actually issued a warning. So in many cases that will actually take years because often these attacks go unnoticed. So they were compromised, but at least they found this out. And then, as was later to be read in the press, actually some companies, including Lockheed Martin, actually announced that they had been attacked through this way. So they did not say whether anything was in fact stolen. But the fact was that they had been attacked. And so at the same time, RSA actually had to um, replace about 40 million of these hardware tokens worldwide, and Lockheed Martin itself about 45,000 of these. So this was a big security issue. It's certainly one of the larger attacks, and it was a high-profile attack because it was such a actually heavily fortified network by a very sensitive company. Um, but still, it succeeded. And I'm showing you this because if you look at how these cyber attacks usually work, they pretty much always have the same scheme. So you first find a vulnerability or place a backdoor, then you inject some malicious code, you circumvent detection so that you are not directly being kicked out of the network again. Then you do this digital shoulder surfing, so you survey the system and fake more machines if required. And in the end, you execute the payload. So the payload is basically what you designed the attack to actually do, right? So you might actually compromise a machine, or you might steal some data, whatever. But if you look here at the line that I underlined, it all starts with a vulnerability, right? So if we had ways to detect and avoid vulnerabilities, all the rest would not work anymore, right? Or at least it would become a lot harder. I think we are a long way away from getting systems that are even just close to 100% secure. By now, I would be happy if people would at least find the most blatant vulnerabilities. But the fact is that any vulnerability that you find and that an attacker cannot exploit is making attacks a lot harder. And at some point, the incentive for attackers might be so low that they actually don't go about the attack in the first place. All right, so the system doesn't need to be 100% secure, but it needs to be secure enough. And finding vulnerabilities can help big times when it comes to that. Interestingly, there's a study by the Department of Homeland Security, but also others, that show that more than 90% of all the current cyber attacks succeed because of vulnerabilities in the application layer. So yes, there is cryptography being broken. Yes, there are network components being broken. In some actors where in some cases where nation state actors are involved, you might even see attacks on security sensitive hardware. But in the vast majority of cases, and that's certainly 90%, probably even a lot more, people are exploiting application level vulnerabilities. And that's not because, they like it to break applications. That's because these are the low-hanging fruits. So attackers, they typically like to go for the easy way, right? So if a door is open, you will just go in there instead of breaking a window, right? I think that's just natural. And there are often that many different kinds of latent vulnerabilities in application code that the attackers don't have to look anywhere else. And so it means the application level is really something that needs to be secured. And we need to be able to fix application level vulnerabilities. And that's where static analysis can really make a big difference. And this is also the research landscape in that we operate. This is also one of our key motivating factors for why we do what we do and what I'm teaching you in this course. If you want to find out more about our research, we have our website, of course, where you find our recent papers. But occasionally, we are also using Twitter to announce new presentations or papers that we have been working on. And I encourage you all to take a look at that and see if you find that interesting as well. If you do have any questions about this or our research in general, please feel free to contact me at any time. I'm always happy to chat about this. This is what I wanted to say about the motivation for why we do static analysis, why I think it's really important. The plan for today, or I should rather say for the rest of the week, that is that I will also be giving you some more administrative information about the course. That part I won't be putting onto YouTube because it's not important for people who join into this channel, in case you're wondering. But then I will also be talking more about intermediate representations like I already discussed. See you then.